Let's try this. Okay. Hey, everyone. So welcome for this first session of the Quantum Global Public Goods Project from the EPFL Quantum Computing Association. So I will just address a few words about the scope of the project today. So we're launching a project, a series of talks, basically trying to assess the basic requirements to tackle a project which might indeed lead to very interesting results. The scope of the project is to link, how can we link quantum theory, quantum entanglement more specifically, with game theory perspectives. We know that game theory has perspectives in economic situations, lots of human interaction description, and potentially also decision making. And we want to know if quantum computing and quantum communication protocols might help in the matter. So today, the presentation we are tackling is a presentation of an entanglement resource itself. And so we have two speakers today from the association and EPFL to talk about this. So those are Fabio and Aman. Fabio is a PhD student who arrived very recently at EPFL. And he will present himself and what he does more in depth. And Aman is the current vice president of the association and a computer scientist, finishing his bachelor this year. So thank you guys for preparing this talk. We're super happy, excited to see what you have come up with. And Fabio, if you who's want to start? Fabio, you starting?
Aman.
Yeah, Aman is starting. So please lead the floor.
Hey everyone, so welcome to today's presentation. So this is the first one in the series of Quantum Global Public Goods, and today we're going to present quantum entanglement along with Fabio. So as Arthur said, I'm a bachelor student in computer science and currently in my last semester, and I'm following some quantum computing courses, and yeah, I'm really interested in the subject. So I'll be presenting the basics of entanglement, and then Fabio will continue with how to quantify entanglement. Okay, so I can start. So yeah, just what it will look like. I'll start with an overview of multi-qubit states, and then we'll talk about entangled states. And we'll have a look at the EPR paradox and some theories which came out of it, and then how John Bell came up with his experiment to disprove the theories. And then Fabio will talk about how to distinguish entanglement and how to quantify it. So let's get started. All right, so this might be, depending on your background, I guess this might be too basic, or it can't be too advanced, I would say. It's pretty simple. So single qubit states are represented using kets. And in the computational basis, you have two basic kets, which are 0 and 1 ket. And this is also the Z basis, but we call them the computational basis because it's analogous to 0 and 1 in classical computing. And then these kets are basically two-dimensional complex vectors, but we write them, so this is the shorthand for just a vector. And we can generalize the concept of a 1 qubit state. So a qubit is a quantum object which behaves using the laws of quantum mechanics, and then it is a two-level system. So it can go from, so here the two levels are 0 and 1. But the interesting part is that it can also take values between 0 and 1. And in fact, it can take any values such that, so alpha 0 plus beta 1. So where alpha and beta are complex constants. So as you can, but the only condition is that the final state is normalized. So yeah, there's a huge range of spectrum for a state, a quantum state. Now we can generalize this concept of a single qubit state to a multi-qubit state. So when you want to work with more qubits than one, using the tensor product. So for example, if you have two states, psi1 and psi2 with their own constants, they don't have to be the same, but they could be the same. To express the combined state of these two qubits, we use the tensor product as seen here. Which is, so it can be computed as follows. So I just plug in my values for psi1 and psi2, and then we can compute this product in a distributed manner. So it follows the distributive law, and we end up with, so 0, 0 here is a shorthand for 0 tensor 0. So that means the same thing, it's just easier to write. And so in this case, for these two particular qubit states, we obtain with the general 2-qubit state. So any 2-qubit state can be written like this. Well, we'll see those who can, those which cannot be soon. But so yeah, this is the general expansion of if you take two single qubit states and then you make the tensor product to express their combined state. So what are separable states? So these are in fact just the states we saw in the previous slide, where you take two single qubit states and you express their combined state. So using a tensor product. So this is a circuit from IBM quantum experience. But so what I'm showing here is just 3 qubits, and then you're applying single qubit gates to them. So these are transformations. But the fact that we're only applying single qubit transformations means that these qubits will always remain separable. No matter how many of them you apply, or no matter which ones you apply, as long as they're a single qubit, they will remain separable. So in this case, this circuit might get as large as possible, but it's still separable. And what we mean by separable is that at any point, so here, wherever you want, they can always be expressed as some state psi1, tensor psi2, tensor psi3, right? So it's some different states. So now the question is, are all multi-qubit states separable? And if I'm asking this question, the answer is no, obviously. So here's an example, the basic example of how you can produce a state which is not separable. So we start with 2 qubits again. So initialized in the 0, 0 state. We apply a Hadamard gate to the first one, so 2q0. So the Hadamard gate puts the 0 in a superposition of 0 and 1. So you obtain, at this point, you have an equal superposition, right? And then we use the control NOT gate, which is summarized in this table. All it does is that it takes the control qubit and sees, and if it's a 1, so if it's in ket 1, then it applies the next gate to this other qubit, which is the target qubit. So as we can see in the table, if the control is 0, nothing changes. But if the control is 1, the target qubit is flipped. Right, so in this case, the target qubit is initially 0 at this point, and now we apply the control NOT. So let me just express the state at this point. So let's call it 1. So at the 1 point, the combined state of the 2 qubits is a tensor product, but using the shorthand, we can write it as 0, 0 plus 1, 0. So I'm using the left indexing because this one is Q0 and this one is Q1. So we see that Q1 is always 0 at this point. Now we put a second barrier here, and let's say at this point the state is 2. So what has happened now is that we have applied a CNOT gate. So in the case where the first qubit was 1, we're going to flip the second qubit. So we end up with 0, 0. And so in this case, nothing happens because the control was 0. But in this case, the control was 1. So we're going to flip the other one. And we end up with this state. Now, how do we know? So this state I claim is not separable, which means that it cannot be written down as a product of 2 states. But how do we know that? So we can actually show this using a very quick proof. So if you compare this state with this general formula we had for separable state, if you try to equate these two, so I'm putting the same state here as the other slide, we see that alpha gamma, this product, is not equal to 0 because it is contained in the final state. And so is the case for beta delta. This is also not equal to 0 since it's also contained in the final state. However, the alpha delta product is equal to 0 and beta gamma is also equal to 0. So this, we see that leads to a contradiction because if you try to put alpha over gamma delta, for example, in this first equation as 0, then the other one of these two falls apart, and then we see that there's a clear contradiction here. So this is why we know that this state, the state we produce using the circuit, the most basic, so it's a Bell state, is not separable. And these states, we call them entangled states, the ones which are not separable. All right, so after the formulation of quantum mechanics, so Einstein was famous for being troubled by this theory. And so along with Podolsky and Rosen, so these three scientists, they wrote a paper where they explained that there's a paradox. And the paradox was, so if you assume these two properties, which are the localism and the realism, so quite philosophical concept, and along with the speed of light limit that Einstein came up with, you run into a paradox because of this entanglement property. And that's, so we'll have a look at this now. So localism is a concept which says that no action may propagate instantaneously between spatially distant objects. So if two objects, or so two qubits, let's say, are spatially distant, like they are located different, far apart, then and anything you do, so any action or any influence from one qubit to another cannot travel faster than the speed of light. It has to follow the speed of light limit. So everything happens locally, or if it doesn't, then it has to obey the speed of light limit. And then the other concept is of realism, which is even more philosophical, I would say, where, so Einstein said that if you can accurately forecast the outcome of an experiment, which means that you can say that with certainty that this is going to happen, and then it does happen, then that means that there must be something real about it in the first place, that it's not just pure chance. So we'll see how this relates to entanglement. All right, so we go back to our same circuit where we entangle these two qubits, but it is still possible to take these two particles, which we entangled, well, whose states we entangled, and take them apart. So let's say we take one of them to Mars and the other one we keep at EPFL. And so the average distance between Mars and Earth is like 3 light minutes. And let's say that after doing this, we perform a measurement, let's say at EPFL or at Mars, doesn't matter. Let's say we perform a measurement first at EPFL. So since the state was, so just a reminder, the state was this superposition. Sorry for the bad handwriting. So what we see here is that when we measure the state, let's say we measure only one of them. In that case, if we obtain a zero, so let's say we measure the state, the Q0, then if we obtain a zero in our measurement, then, so when you measure, actually you obtain the eigenvalues, you would obtain 1, but so let's just say we obtain the state 0 in our measurement, then we know that the entire state, the combined state of the two qubits, has collapsed into this state. So this automatically implies that the other qubit is also in state 0, so its state has also collapsed. And this action happens instantaneously. So as soon as you measure your qubit, you are sure that if you now measure the qubit on Mars, so let's say we measured a qubit at EPFL and it gave us 0, then we instantaneously know that the qubit on Mars, when measured, would also give us a 0. And so that's where the contradiction comes in, because supposedly there's this transmission of information between these two qubits, which is happening not locally and which is happening instantaneously. So it's not taking 3 minutes. It's happening in 0 seconds, like instantaneously. So that's why that's where the contradiction comes in, and that's why the paradox comes in. And so Einstein and these other people were not very happy about this, and they were saying that the quantum mechanics, so the formulation of quantum mechanics, was incomplete, and that it was missing some more explanation, and that maybe we could explain this using some extra hidden variables, which means that maybe that the qubits already, so the fate of the qubits was already decided before they were taken apart. So that brings us to the theory of hidden variables, where Einstein famously said that, yeah, quantum mechanics is incomplete and there must be some sort of hidden variables. And so what this would look like would be, for example, when you entangle them, the qubits, like sort of, so this is just a, I guess, like a comical way of saying it, I guess, that they talk to each other when the qubit, so the first qubit says, okay, let's both show up as 0 when we are measured. And so they both agree before they are taken apart. And then when they are measured, we think that they communicated faster than the speed of light, but in fact, they were both deterministically collapsed to 0. Or in fact, they were all along zero all along, because you would measure 0 whenever you measure. So And that, so Einstein was saying that there must be some other explanation than this instantaneous propagation of information. And so, what he didn't give a theory, another explanation. He was just saying that there must be some other hidden variables which would explain this, which would determine the state of these qubits from the beginning. And so this also takes in the concept of realism, because Einstein also did not like the concept of the old man playing dice, because in quantum mechanics, when you are measuring this, so when you're measuring the state, they have an equal chance of collapsing to 0 or 1 because they are in equal superposition. So Einstein also did not like this. So he was saying that it must be the case that their fate or their outcome has to be predetermined. And that's where he brought in the concept of realism, because if you are predicting, so when you are measuring one qubit and let's say you obtain 0, and then you are sure that the other qubit has to be 0 as well, there must not be a random chance, there must not be randomness behind it. It must be determined. It must be a deterministic process. There were some controversies around this theory, and then people were not really able to explain why this transmission of how this collapse was happening instantaneously. Then came in John Bell, who introduced this theorem, which proved that quantum mechanics is in fact incompatible with the local hidden variable theories. So this was a huge breakthrough, because he came up with an experiment which would actually enable us to distinguish between classical and quantum correlation. So correlation is basically some link between the outcome of two experiments. And so we saw that when we are measuring these entangled qubits, we always obtained, for example, a perfect correlation in this case when they were in state 0, 0, and 1, 1. So a classical correlation would be of the sort that their state was predetermined, and that they were, from the beginning, they were in 0, 0 or 1, 1. And the collapse did not happen when they are measured. So that's what classical correlation would say about this experiment, whereas quantum correlation would say what we have been saying for the previous slides, which is that the collapse happens when they are measured. So Bell's experiment was the following. So as you can see in the image, so you produce an entangled pair of photons at the source in the middle, and then you send them off in different directions. And so as you can imagine, Mars and Earth, for example, well, it's not realistic, but you can imagine it. And then these both quantum states are measured by the two parties, and then you can change. They are measured by these detectors whose angles you can change. So depending on which angle you measure the state at, you get different results, because you are using a different measurement apparatus. But either way, no matter which angle you use, you always obtain the eigenvalues of the operator. And for all these operators, the eigenvalues are +1 and -1. So using this experiment, you can, so depending on what values you get in the two measurements, you can quantify the correlation between these two. So how many times they are given the same value and how related they are, right? So now you can test both your classical correlation theory and the quantum correlation theory. And in fact, the classical correlation theory, as seen on the graph on the right, predicts this red line, which gives you a perfect correlation if they are measured, for example, at a 0 angle, which means that, so at 0 angle means that they are measured in the same direction. So that does explain what we were saying before, right? It does explain that they're perfectly correlated and then you always get the same result. So for now, classical is still doing okay. If you put them at a 180-degree angle, then it produces again like a opposite correlation, but still perfect correlation. So it's still doing okay. But when you look at angles which are in the middle, so let's say you look at 45 degrees or 135 degrees, that's where the difference comes in. That's where the quantum theory predicts a correlation which is higher than the classical than that predicted by the classical theory. So as you can see that at these where there's the stars on the graph, so at these points and so on, the classical correlation only allows values of 0.5 plus or minus, but quantum mechanics allows values of plus minus square root This should be actually 1 over square root of 2. Sorry about that. So it allows higher values than 0.5. And this is in fact what this is in fact verified by actual experiments that we do get correlations which are higher than 0.5. And we actually get the same correlation as predicted by the quantum theory. So this was basically a debunking of Einstein's local hidden variable theory, because they were all based on deterministic processes, I guess. This was conclusive proof that there could be no local hidden variable theory which could explain what's happening. So it ruled out basically all theories. So we are left with our quantum theory. And yeah, so this was a huge moment for quantum mechanics. So I'll let Fabio take on from here. I'll let you share your slides then.
Yeah, I'll share my screen. It's okay. Okay. Here we go. So can you see the slides?
Yes, we do.
Okay. Okay, so hello everyone. My name is Fabio. Thanks, Adam, for the very nice introduction about the basics of entanglement, and also you described very well how historically the theory has been developed and all the different ideas about this topic. I'm currently working on electron spin qubits, of course, for quantum computing applications, and I might work in my future also in the Hall spin qubits. These are kind of devices where I'm trying to use the basic tools that quantum physics gives us, such as entanglement, to build quantum gates that could be made faster and smaller in silicon. If Adam did a presentation from the quantum circuits point of view, he showed some quantum gates and other stuff that are actually related to our project. I would say that most of the papers on this topic comes from the physics world. This means that if you really want to dive into this theory, you should know, you should have some solid basis on at least the formula and the criteria that people in this field are using. And that's why in my part of the presentation, I'm trying to give you an overview of the most important, let's say, concept as results on this topic that I found basically in all the papers that I've opened on this topic. And the important thing is that what I'm going to describe is valid is described in a very general approach. And therefore, it can be applied to many systems, but also, of course, to the quantum computing world. So let's start with the first question. The first question is, given a quantum state, is it separable or entangled? Adam gave us some hints about this. And I will show you that from the theory point of view, there are some criteria that most of the people divide in two classes. Some of them are called operational criteria. Others are called non-operational criteria. Well, the second ones are just a name to describe what people have invented to experimentally understand if a system is entangled or it's separable. Let's start with a definition that actually Adam already gave. So we know that a state Psi is separable if it can be written as the tensorial product between two basis states. Otherwise, it is entangled. You will see, if you will dig into the literature, that most of the works are actually explained not in the basis point of view, but using matrices. This is because when the physicists very like to describe things in a general way. So most of the formulas are given for n dimensional systems. And so where the dimension gets very high, it is not very comfortable to use vectors. That's why they're using matrices. So let's introduce the density matrix. The density matrix is here expressed with the letter rho. This is just described by the summation over all the tensorial products between the operational states of two subsystems in this case. So we have one subsystem called A and one subsystem called B. where pi is, these are just real numbers that describe the probability of finding the system A in the state I and the system B in the state I. Let's start with a simple example that is really related to what Adam said in this presentation. So if we consider now, instead of photons, 2 qubits that builds up from the spin of electrons. So you know that the spin of electrons are alpha spin particles. So if we take one electron, its spin state can be described in the basis in the spin basis as up or down. And for another electron that we call B, of course, we have the same set of the same basis state. If you want to describe the system that builds up from the interaction of the 2 electrons, we need to take the tensorial product between the 2. And let's have a look at this Bell state, which is actually the real state that Aman showed in handwriting, in his handwriting. If you try to manipulate this formula, there is no way that you can describe this state in the formalism of the density matrix. This is because the state is not separable. When the first spin is the first electron is overlapped with the wave function of the second electrons, experimentally there is a way to make this entangled state. And when the state is entangled, again, the 2 states are not separable anymore. And from the experimental point of view, as Aman said, when Alice, in this case, so Alice stands for our subsystem A, measures, before Alice measures, Bob can either obtain a plus or minus sign for the spin states. But after we know and we measure the subsystem A, the outcome of the subsystem B will collapse to the opposite state, showing an interaction between the 2 substates. So this is what happens when 2 substates are correlated and entangled. Here I've somehow just a definition of the density matrix. I already described it. So how can we theoretically understand if a density matrix, so if a state described by the given density matrix is separable or entangled? Well, if we use the definition that I put in the first slide, this is valid, but to understand and to prove this definition, we should know all the elements of the density matrix, right? And actually, it is possible with some experimental tool to calculate all the elements of the density matrix, but it is very hard work. However, there are some tricks that give us some hints to understand if a system is a separable system or entangled one. So I sum up 3 different criteria that are the most basic one that I found in literature. The first one is called the Perez-Horodeiki criterion, that people call the positive partial transpose. So given a density matrix, we just have describing the overlapping of 2 subsystems that in our case could be 2 photons or 2 electrons with their spins. We just transpose the part of the density matrix that comes from the system A. Okay. If we compute the density matrix of this separate matrix coming from system A, it can be shown and it can be demonstrated that it can be put in this formula, of course, when only the part coming from A has been transposed. Oh, sorry. And it is it has been demonstrated that this definition is always greater than 0. This is a criteria that is valid for 2 and 3-dimensional subsystems, and it is necessary and sufficient to prove the separability of the system. So basically, if we have a system that builds up from 2 different subsystems, and we know the density matrices, we can compute the density matrix of the whole system. We take the transpose of the part of the matrix density coming from one of the two subsystems, and if the system is 2 or 3 dimensional and that matrix is greater than 0, then the system is separable and it is not entangled. Another criterion is the reduction criterion. So if rho, so if we have a density matrix that it has been proven to be separable, then we know that these formula are greater than 0, where this formula just let's say builds up from the tensorial product between the density matrix of subsystem A, so from our spin qubits or from our photon, minus the density matrix of the whole system. Okay, so we have that rho A and rho B are the reduced density matrix for the two subsystems. This criterion is somehow correlated to the most famous one. That's why I put this one in green, which is the majorization criterion. Although this one is only a necessary criterion, it is not sufficient even for 2 or 3-dimensional systems. Well, to understand these two criteria, I put a sentence that I found in one paper that states separable states are more disordered globally than locally. So this is a state that I will show you in the last slide. It's really describing something correlated to a separable state and not to an entangled state, because in an entangled state it will be the opposite. So let's have a look at this criterion. If the density matrix is separable, then we have that the vector consisting of the eigenvalues of the matrix of the density matrix of the whole system is always minor than the vector consisting on all the eigenvalues of just the density matrix of the local subsystem. This, of course, is valid for all the subsystems building the whole system. Okay. So we have 3 criteria to characterize if a system is separable, giving a density matrix. Okay. So what about the entangled system? How can we distinguish an entangled system without proving that it is separable or not? Well, we have some tools. The first one is called entanglement witnesses. It is the most famous one. And it states that a density matrix rho is entangled if and only if there exists an Hermitian operator W, so that the trace of that operator applied to the density matrix of all the system is minor than 0, whereas the trace of the same operator applied to the density matrix of a separate subsystem is greater than 0 for any separable state. This is a very powerful tool for us because it means that if we already know the density matrix for our spin qubits or for the state of our photons, so for the polarization and so on, and we know also the elements of a density matrix of a system that builds up from the combination of different subsystems, we can understand surely if this total system is separable or it is entangled, just based on this definition. So the question is, how can we construct this W operator? Well, there are some tools that have been also experimentally demonstrated. Most of them rely on the fidelity operator, which is usually employed to measure the distance of a general state from another state. With some basic calculation, you can understand that the trace, starting from this definition, sorry, of the W operator, where alpha is just a real number, and this is the external product between the bases of the state. Doing some basic calculation, it is possible to demonstrate that the trace of the operator applied to the density matrix shows a linear relation with the fidelity operator. So, of course, it's difficult to explain all the details just with this formula. But the important thing that I would like you to notice is that this is just a linear relation, and we just have to prove if this relation is greater or less than 0, if it is positive or negative. So if we set experimentally in some way the value of our real number, and we manage to create an operator that tells us if our state is very distant from another state of reference or not, we can say if our state is entangled or not. Okay. And the good news is that it has been shown and it has been proved that for every entangled state, it is possible to construct an entanglement witness. So this operator is always possible to construct. So now we have some tools to understand if a state is separable or if it is entangled. So if we discover that the state is entangled, how can we measure and how can we quantify the level of entanglement between the subsystems that builds up the total system? Well, there is this definition, which is the most used one. It's called the von Neumann entropy. We can make a clear analogy with the Shannon entropy from the basic physics of and the basic thermodynamics. So the logarithmic terms is not, I mean, we should not be surprised to see a logarithmic term because, of course, it's an entropy. The only thing is that we have to compute the trace of the reduced matrix, the density matrix of our system. So what is the trace? It's just the sum of all the elements on the diagonal of the matrix. So just a hint, if you get lost with this kind of notation, just remember that rho is a matrix, whereas all the bases, so the cat and the bra, are vectors. Okay, so even if you have never followed a quantum physics course, you can always think about this stuff with matrix and vectors. So we know that this von Neumann entropy, it is 0 for an unentangled state. And if I look at this formula, it is convex. What does it mean? It means that the entropy of the sum of the entropies of the subsystems building the total system is always greater than the global one. So if I go back to the slide about the operational separability criteria, there's this sentence that states, separable states are more disordered globally than locally. Okay. If I look at this definition here, we see that for the entangled state, it's just the opposite. So they are more disordered locally than globally. I put also the definition of the Reinhai entropy. Actually, I have no idea how to pronounce this name. I put this formula just because all the discussion that I've made is more related to two-dimensional or three-dimensional systems, whereas this formula is valid for n-dimensional systems. So I put it just in case you got lost reading some others paper. So to sum up what we have said, entanglement is a fascinating and unique property of quantum mechanics, of course, that does not exist in classical computing, in classical system. How can we measure the entanglement? Well, there is the definition of the entropy, which is just the one that I showed in the last slide. And in principle, this level of entanglement can be measured in condensed method or called atom experiments. So these are all the pros, whereas what are the cons? A lot of math is needed to describe what's going on. So I strongly suggest to have a look at one of the publications describing this kind of stuff. You will be surprised about how many details are in there. And so I just try to give you some hint that could help you to understand the basic tools that people are using to describe this kind of effects. With this, this is the end of the presentation. We put some references that we will share with you, of course. And we are open to any question.
Thanks a lot for this amazing presentation. Really, I think this was very insightful on many, many grounds. I have a bunch of questions of my own, but before me, is there any question from the audience that you might have? No? Okay, so in the meantime, I will ask mine. So my first question was about the entanglement witness. So if you go back to the definition of the entanglement witness, there is a dependency on an arbitrary state psi that you fix to distinguish the fidelity of the state. So in practice, so to construct an entanglement witness like this, we would do we need a specific state, or it can be any arbitrary state, and we try to build this operator based on the state that we've chosen, based on the fact that we can evaluate the fidelity compared to this arbitrary state. You're muted, Fabio. Yeah.
Sorry.
Yeah.
As I was saying, that experimentally, of course, you need to prepare your state. Mm-hmm. And that will be the reference state at which you will apply your fidelity operator.
Right.
So this definition is valid in general, but in the field of quantum computing, we should know the initial state of the qubit. Mm-hmm. And then if you want to merge the different qubits to build an entangled state, you can compute the density matrix, and you can apply you can construct the witness operator. But you have to know in principle what's the initial state. So this is what I got in my reading.
So the difference between the state that we are trying to measure in this case, so the state rho, which stands for the entangling operator, the state that we would witness the entanglement for. Apparently here the state psi is a pure state, right? So it acts like a state of reference. So yes. In the frame of quantum computing, so would we decide of a state of reference psi and try to evaluate the trace distance based on the obtained density matrix by the operations that we would conduct to entangle the qubits. If I take, for example, the example of a man, I would apply a CNOT gate, and so I would get a perfectly entangled state. And then I would construct an operator based on a pure state, like, for example, the 0, 0 state, for example, then I can assess based on this fidelity, a witness operator.
Yes, this is what I got, at least for the engineering point of view. Then I'm not a physicist, so I'm sorry, I cannot really purely answer to your question. But yes, what you said is what I got from the quantum computing point of view.
Okay, so it's good. And so the alpha is probed experimentally based on the arbitrary state that we...
Yeah, it's a real number, yes.
Mm-hmm. Got it. Awesome.
And another important thing is that since alpha is not 0, this proves that actually you cannot measure every entangled state. So basically, if you have an hyperplane containing all your entangled state, you're cutting this plane with another plane. So, and you can distinguish some entangled state, but all the states that are below that real number in the hyperplane cannot be detected.
Mm-hmm. I see. And to usually measure the fidelity of the state that we obtain, what are the usual experimental techniques that we use? Is it tomography experiments that we assess usually, or benchmarking, randomized benchmarking, or some sort?
Yeah, it's tomography.
Or tomography.
At least in the paper that I was referring to, that is, let me take the references. Should be this one, the Riccardi.
Yeah.
Riccardi Gabriele.
Yeah, it's a very recent one on top of that. Yeah, really cool. I saw this one coming. I got another question. So you were mentioning when you assessed the measure, the different measures, that it was valid for 2 by 2 system of 2 by 2 and 2 by is it 3 by 3 that you meant, or?
Yes, 2 by 3.
2 by 3. Okay, so yeah. It's a 2-level system with a
combined with a 3-level system.
I see. Got it.
Yes. So actually, the most powerful one is the entanglement witness technique, because the other one are just necessary and conditions.
Yeah, because in the end, when we measure, so one thing that we could add maybe, because we went through the partial trace very quickly, is that it's an actual operation that may that may require a measurement, right? A local measurement from one of the two qubits. For example, if we have two qubits, the partial density matrices that we would obtain results from a measurement in the computational basis or any
Yes.
basis
Yes.
from the other qubit.
Yes.
Uh-huh.
Yes.
Yeah. Yeah, so that brings us to, yeah, for example, if we have A and B, so Alice and Bob, like if Alice decides to what we call trace out her qubit from the system with that she shares with Bob, Bob would be left with another density matrix, which would result, okay, if it's a perfect entangled state, it will remain a pure state, like most likely a 1, 1, 0 or 0, 0 based on the result we got before, but depending on the amount of entanglement, we can end up with different quantum states, reduced quantum states symbolized by this density matrix for the second system.
Yes, right. Indeed, from the quantum computing, from the quantum gates point of view, is something very complex to see this.
Yeah.
That's why I said that at the beginning that this theory is just put in a very generalized way without scheme of gates and so, because otherwise it would have been too much complicated.
One last question I might have, so maybe outside of the scope of this specific presentation, but it might help us for the project in the future, is once we entangle the state, like with using a quantum circuit, a deterministic quantum circuit, is it possible always to reverse the entangled state and to go back to other separable states? Like we can apply of course, the unitary in reverse, right? My question would be if we apply, for example, an entangling operation, like let's say we entangle the qubits with a perfect Bell state, and then each of the players, or Alice and Bob, apply a unitary rotation on their own qubit. Can we always find an operator, a unitary operator, which might be using other entangling gates that might reverse the original entanglement, or like is it deterministic, or I would rephrase that. Would there be a way to find such operator based on the information that the strategies that are being, so what I call strategies is the gates, the single qubit gates that Alice and Bob would represent. Could we find a systematic way of trying to find a unitary gate that cancels the amount of entanglement and leaves us back to a separable state? So that would be the question. I don't know if it was clear enough. I should maybe show it into a circuit, but
in this case, like if Alice and Bob are doing their own unitaries, they could just reverse first their own unitaries and then you just apply the same reverse circuit as you did to entangle them, for example.
Right. So, but the operation that we use to entangle their system in the beginning, based on their, let's say that, for example, the users, the Alice and Bob, like apply a different unitary operation on their own qubit, so a single qubit rotation. So obviously, the whole system would change since the qubits are entangled in a way that, like the unitary of Alice and the unitary of Bob would contribute to increase the entanglement amount or decrease the entanglement amount, right? It would like change the amount. It would still be entangled, but the application of these single qubit gates at both levels would eventually like modify the level of entanglement. And the question might be, could we end up at the end with a removal of entanglement, like trying to find some de-entangling operation, which might not be trivial to find, of course, but can we always find one? So that would be a question.
Well, I don't know, I may be wrong, but as far as I know, everything is reversible unless you measure, right?
Mm-hmm, right.
So in theory, it must be possible.
Yeah. So in this case, we could think about, so if we go in the frame of now we're talking concrete about the project, right? Like if you recall, so we'd like the parties to make a choice, a strategy into the game theory, what we call a strategy in the game theory, which is encoded into a unitary operation. So we give a qubit to Alice and Bob, let's say, or state 1, state 2, and we want them to give, we want them to put a choice on their own qubit. And the question is, of course, the goal is that their choices that will the strategies that we employ will correlate the amount the strategy of the other without them knowing it, of course, because it's kind of a pre-contract linked to entanglement. Now the question is, in the end, we want to retrieve a classical strategy, right? When we measure, each party should receive a classical strategy in return. So of course we could make statistics, so we could think about mixed classical strategies. We'll see that I think next week about game theory and everything. But if we retrieve this amount, if we make the measurement of an entangled state, is this the same result on the correlation that if we try to operate a reverse engineering by saying, okay, I want first to de-entangle the qubit and leave up with a separable state. And so that this will leave up with a new strategy, which was not the original one by which Alice and Bob desired in the beginning, but which might be decided upon the mutual decisions and increasing some kind of cost function, because in the end we want to improve some kind of cost. And so this new unitary, the one that we would use to de-entangle the states, would be calculated to optimize this cost function. Do you see the process? So we could think about here implementing some kind of optimization, so making multiple times the experiment and saying, okay, how can we use these entanglement witnesses or something like this to make sure that the state that we will retrieve before measurement is a separable state, to make sure that we have in the end separable strategies that were modified by the behavior of everyone. So if I present quickly my slide that I was having, so let me find it very quickly. On the project, should take a second. Here we go. It should be here. Yes, here. Everyone can see my screen, right? The presentation. Yeah. Oh, awesome. So yeah, as I was saying, so this is what we imagine, right? So we have some kind of entanglement operation. If let's say we want to aim for the perfect entanglement, so we would have a GHG state with n parties. Let's stay on 2 to make it simple. And then we give the freedom of applying one unitary, U1, which only the player 1 would know, and the U2 would be only the unitary that the second would know. And then what might come, the question I ask here, and so this has to be cleared out in the following weeks, but what is the strategy that they should retrieve? So my initial guess was that the strategies they want to retrieve here is some kind of classical or mixed strategies, for example, that would be returned from the different strategies here. And this de-entangled operation would act so it would not be the same operation. It's kind of a mistake, because what we want to do is aim for a separable state that would end up with, okay, everyone lives up with a decision, but which might kind of might take it into account those parameters, so those unitaries, and optimize the results such that we optimize the cost function. So the bet would be, okay, for me, there are 2 ways to think about it. Either we say, okay, like we remain into an entangled operation, but then we know that because of the partial trace, the system of one will directly collapse the result of one another. Instead, if we return to an de-entanglement operation, even if the new separable state is nothing like, of course, the original separable state, and this is the goal. But in this case, it doesn't matter who measures first, right? The measurement will not be impacted by any of the parties. And so I wonder if this might be something that we would want to, in the end, have classical, retrieve strategies that benefit, like on top of maximizing the utility of each of the parties, trying to maximize the global utility in the sense of preserving the public goods thing. So those are questions that we should maybe think about. And I'm sure we will get to come back to this question when we get a bit more into the game theory perspective and how to assess, the utility of the players and everything. But for me, I was understanding this de-entanglement operation is important if we want to ensure that there is some kind of fairness between the parties, in the sense that if one measures, it will collapse the state of everyone else into a decision that might be like kind of arbitrary, and we might have some random random selection. In the end, if we return to separable states, each one does its measurements, and based on the statistic that we would do, we would return with some kind of state for each one. So a mixed strategy, so a superposition of 0 and 1, if we stay on a qubit, that would end up to the optimized strategy to adopt. For example, I would think, yeah, so this is a bit going a bit ahead of time, so let's keep it for the next presentation. But yeah, I think we should keep this picture in mind. And regarding the witness, I was particularly interested into the witness entanglement, like trying to see if there could be something we could dig into some kind of code analysis backwards. So we make a series of experiments with different unitaries for each of the players and see if we can come up with recreating separable states at the end by performing some kind of additional operation here. I think that would be interesting to see. Can we like systematize in a bit, like automate the fact that we can create this entanglement operation, de-entanglement operation based on the knowledge of the unitaries that are being sent here. So this could be an interesting project of its own, by the way. Like I think it could be, it's going to be part of the project, but to say, okay, I want to create, no matter what, a separable state here, and then would come an optimization, of course, under constraint. But this could already be an interesting question. And we shall see afterwards if there is indeed an advantage in quantum strategy overall by proceeding only by this way, or if there could be other hypotheses to be used in this framework. Cool. Yeah, for me, for now, I don't have any more questions on that. So by the way, I will, so I should mention, so this video, if everything worked well on the recording, I will put it on YouTube, and the slides will be available on the drive of the association as well. If someone wants to access the references or everything, it can be found in the drive of the association directly. And again, for the potential viewers of this video, you can always reach us for any questions at quantum@epfl.ch. So this is in the case, like we go worldwide with our project, but in the meantime, let's keep it realistic. But anyway, it was great to have this first presentation. I think it was very complete. Quick feedback, because we are not so numerous, so maybe we'll close the recording here and do the feedback offline. So thank you everyone for joining us in this presentation, and hopefully see you next week for the next presentation. We will deal with the game theory perspectives.